In this video, I will explain the operating principle of a nuclear reactor. Let's first recap a bit the fission chain process in a nuclear reactor core. If a slow neutron hits a uranium-235 nucleus, it will lead in 9 out of 10 cases to nuclear fission. In this process, 2 fission fragments are produced, the brown bullets, and on average 2.5 fission neutrons. The probability for a fast neutron to be absorbed by another uranium atom is very small, and therefore we have to try to slow down the neutrons by letting them collide with light nuclei, like hydrogen or carbon, a process which is called moderation. The slow neutrons, after moderation, can easily be absorbed by uranium-235. Of course, in each generation, we need an equal amount of fission reactions for a constant power production. So the other neutrons will have to leak away or need to be absorbed, for example by the control rods or by the uranium-238 in the fuel. In the latter case, uranium-239 is produced, which decays after 2 steps into plutonium-239, which is also fissile and which can be fissioned in the next generation of fission processes. The fission process takes place in a nuclear reactor core, which is positioned in a reactor vessel on this figure. The red-yellow circuit is called the primary loop and contains water with a pressure of 150 bar and temperature of about 300 degrees Celsius at the core inlet and 330 degrees Celsius at the core outlet. The heat is transferred to a secondary loop with lower pressure, leading to the formation of steam that drives the turbine. A generator connected to the shaft of the turbine produces electricity. After expansion, the steam is condensed to water and pumped back to the steam generator. On top of the reactor vessel, you see the control rods, which contain neutron-absorbing materials and which can be inserted in the reactor core to control the reactor power. In addition, there is boric acid dissolved in the primary water, acting as a neutron absorber. The concentration of it can be reduced slowly during operation to compensate for the buildup of the fission products in the fuel and for the reduction of the fissile isotopes during burnup. Here you see how the fuel looks like. Small fuel pellets with a height of about 10 mm and diameter of 8 mm are stacked upon each other in a gas-tight fuel cladding. See the middle figure. The fuel rods are assembled together into fuel elements, and water flows through the space between the fuel rods to moderate the neutrons and to take away the heat. Another type of reactor also works with water as a coolant, but at a lower pressure of around 70 bar and a temperature of about 285 degrees Celsius. As a result, the water starts to boiling in the reactor vessel, and the steam produced drives the turbines directly. Because both the pressurized water reactor and the boiling water reactor use ordinary water, also called light water as a coolant and moderator, they both belong to the class of light water reactors. This figure gives the number of neutrons per absorption in a fuel nuclide. It includes the effect that some neutron absorptions do not lead to fission, but to neutron capture. For a stationary fission chain reaction, the value of the number of neutrons per absorption should be larger than unity, because at least 1 new neutron is needed for a fission event in the next generation. If the line is above 2, there is 1 neutron left to convert uranium-238 into the fissile plutonium, or to convert thorium-232 into fissile uranium-233. In principle, breeding is possible then, meaning that the number of fissile isotopes in the fuel increases. As you can see, this parameter is strongly dependent on energy. If the neutron initiating a new fission is thermal, the thorium fuel cycle is most beneficial, while in the fast energy range, the uranium-plutonium fuel cycle has preference. In that range, the plutonium isotopes give considerably more neutrons per fission than the uranium isotopes. Here we show the principle of the fission chain reaction again. Let's first simplify the scheme a bit by omitting in the plot the two intermediate decay steps from uranium-238 to plutonium-239. In a fast reactor, we use no moderator to slow down the neutrons. Of course, the probability to fission uranium-235 becomes much smaller in this case, and we compensate this by increasing the fuel enrichment from 5 to about 15 to 20% in a fast reactor. In this way, we can compensate for the lack of moderation and a fission chain reaction is still possible. Here we see the scheme for a fission chain reaction for a reactor fueled with uranium-235 and own-bred plutonium-239. I want to emphasize one important thing. We have seen that the plutonium isotopes produce more neutrons in a fission event if the neutron that causes the fission has a higher energy. And this is highlighted at the right bottom part of the plot. Now imagine we would use plutonium-239 right from the beginning of reactor operation. In that case, we have many more fission neutrons in each generation and the possibility to breed more plutonium than we consume. We have then made a fast breeder reactor that produces more plutonium than it consumes. The concept of a fast breeder reactor is illustrated in this figure. In each fission event, we produce so many neutrons that we convert more uranium-238 into plutonium than we consume. So this video I want to end with a question. What is the maximum number of uranium atoms we can convert to plutonium per fission event?